Lesson 1. Propositions and Symbols. So first, what is a declarative sentence? A declarative sentence is used to make statement of fact, wish, intent, or feeling. For example, I wish for rain. So why is there a declarative sentence for math? Let's learn about propositions. A proposition is a declarative sentence that can be classified as true or false, but not both.
Let's now talk about the two types of propositions: simple proposition and compound proposition. A simple proposition conveys one thought with no connecting words, while a compound proposition contains two or more simple propositions that are put together using connective words. So what are these connectives or connective words?
Connectives are used to combine simple propositions to form compound propositions. We can use and, or, not, and, if, then. If the proposition is compound, then it must be one of the following: conjunction, disjunction, conditional, biconditional, or negation.
So let's start with conjunction. It is two simple propositions connected using the word and. We can also use but. Next, we have disconjunction. This is two simple propositions that are connected using the word or. Another is conditional. It is two simple propositions connected using the word if, then. The statement between the if and then is called antecedent of the conditional. The sentence that follows then is the consequent.
Lesson 2. Truth Tables. Let's start with conjunctions. The connective and implies the idea of both. Now, let's draw our truth table. We have our first two variables, P and Q. So for P, we'll write down two T's and two F's. For Q, T, F, T, F. By doing this, we'll have the four possibilities. The equation for conjunction is P and Q. The conjunction P and Q is true when P and Q are both true. Otherwise, the conjunction is false. Our first possibility is that both of our statements are true. Therefore, it is true. Now we have true and false. This is false because only one statement is true. Now we have false and true. This is also false because again, only one statement is true and the other is false. Lastly, both of our statement is false, therefore it is false. Example: let P represent 7 is greater than 5 and let Q represent 12 is less than 0. So we know that our P statement is true and our Q statement is false. Let's find the truth value of P and Q. So let's draw the truth table. We have, of course, our P statement and Q statement. In our four possibilities, the equation for this is P and Q. So both of our statements are true, therefore it is true. We have P as true and our Q is false, therefore it is false. We have false and true, therefore it is false. And both statements are false, therefore it is true. Following the rules of conjunction, since we know our P statement is true and our Q statement is false, our truth table will be false.
Next, we have disjunction. There are two types: inclusive or and exclusive or. Let's talk about inclusive or. It is one or the other, or both. So let's draw a truth table. So we have P and Q and all our possibilities. Our equation is P or Q. Inclusive disjunction is true when at least one statement is true. Our first two statements are both true, therefore it is true. Our P statement is true, yet our Q statement is false. It is still true, since at least one statement is true. Our P statement is false, but our Q statement is true. It is still true, since Q is true. Both of the statements are false. Not one is true, therefore it is false. Example: let P represent I will pass math, and let Q represent I will flunk math. So by this, we already know that only one of it can happen. You cannot pass and flunk math at the same time. Let's draw a truth table. P and Q as our variables and all its possibilities. Our equation is P or Q. As we know, we cannot pass and fail at the same time. So if both of our statements are true, then it is false.
Now we have P as true and Q as false. This is true because you can pass math, and if you do, that means you did not flunk it.
We have P as false and Q as true. This is true because if you flunk math, it means you did not pass math. Now we have our two statements as false. This means you did not pass or you did not flunk math, so nothing.
Next, we have negation. If P is a simple proposition, then P is either true or false, but not both. Not P is false when P is true, and not P is true when P is false. Let's draw the truth table. If P is true, then not P is false. If P is false, then not P is true. Example: this is the equation we're gonna solve, not P and Q. So we have our first two variables, P and Q. Now we have P and Q and not P and Q. Those are our variables. Of course, our four possibilities. For P and Q, we apply the rule for conjunction. So now we'll do the negation of P and Q. So the little trick here is that it's just the opposite of P and Q.
Are conditional and biconditional. So let's start with conditional. Let's draw a truth table. P and Q as our variables, and again, the possibilities. Our equation is if P, then Q. It uses an arrow. If P, then Q is false only when P is true and Q is false, otherwise it is
We
true.
have true and true, therefore it is true. We have our P statement is true and our Q is false. Then it is false, following the rule. Our P statement is false, but our Q statement is true. It is true. Both of our statements are false, therefore it is true. Example, we'll start with conditional. Our equation is if P, then not Q. So we have P, Q, not Q, and our final equation, if P, then not Q, as our variables. So let's write all the possibilities. So first we have not Q, which will be the opposite of Q. We add not Q since it is part of the equation. Now let's start with our equation. We're gonna base it off P and not Q. So our P is true and our not Q is false. Therefore it is false, following the rule. We have both statements as true, therefore it is true. Our P is false and our Q is false. Therefore it is false. We have P as false and our not Q is as true. Therefore it is true. The consequent of a conditional statement should always be true. Next we have biconditional. It's true when and only when P and Q have the same truth value. Let's draw a truth table. We have P and Q as our variables and the four possibilities. Our equation is P if and only if Q.
Our first statements are both true. Since they have the same truth value, it is true. We have our P statement as true, but our Q statement as false. Therefore, it is false because it doesn't have the same truth value. Again, it is false because it doesn't have the same truth value. Lastly, we have false and false. Since they are the same, it is true.
Example, we'll use the equation if P, then Q is biconditional to if not P, then Q. So let's write down our variables. We have, of course, P and Q and the four possibilities. Now we have the not P column, which is the opposite of P. So we have false, then true, false, then true. Our next column is the first equation, if P, then Q. So we're gonna follow the rules of conditional. Next, we have our second equation, if not P,
then Q. So we're gonna use the columns not P and Q. And we're still gonna follow the rules of conditional. Now let's do the whole equation. Following the rule of biconditional, both of our statements are true, therefore it is true. So let's find out. We have true and true, therefore it is true. False and true, therefore it is false. True and true, so it is true. And true and false, therefore it is false. And that would be all for lesson 2.